So today we're going to take some of the electron configuration and ion idea that we learned before the break, review it, and apply it going forward to a way of visualizing electrons and electron structure in a way that's a little more useful for forming compounds. So if we think about why we are working on all of this, well, number one, we need to understand atoms and electron configuration because atoms are what make up chemical compounds, and most of the world is made up of chemical compounds. If we understand atomic structure, then that will feed into how atoms join together to form the molecules that make up things like you, and the ionic compounds that also make up things like you. One can write formulas for these compounds, and in fact that's a big part of the unit coming up. We're going to change formulas and think about how we name them. We're going to take names and translate them back into their chemical formulas. We can predict their structures eventually, and we can use our knowledge to make useful medicines and fertilizers. And we've seen this already when we talked about radioactivity. One of the examples we gave was the radium girls, the girls who painted the glow-in-the-dark dials with the little brushes, and they would lick the tip of the brush to make that brush point stay sharp so they could paint thin lines. Well, the problem with that was they were ingesting radium, which is in the same group as calcium, so it behaves very similarly to calcium, makes very similar compounds, and your body is able to use it as if it is a calcium atom. And it built that radium into their bones. But the radium compounds were not as strong as calcium compounds, so their bones were very brittle. And of course, radium is radioactive. So there was a radioactive emitter right there next to their bone marrow, which caused anemias and leukemia in the radium girls. And maybe if we had understood more about their structure and radioactivity, we would have known that before it happened. All of these things in the long run, we're trying to make things better. So to go from an electron configuration to what's called a Lewis dot diagram, we need to think first about electron configurations. Remember those rules that we had for how electrons are distributed around an atom or an ion. For example, we could use oxygen. If we look at the periodic table, we see that oxygen is element number 8. So it has 8 protons and 8 electrons in the neutral atom. So if we have 8 electrons, we have to remember the first fundamental rule is that nature is lazy, and we have to start at the lowest energy level. That would be the 1s. So we would fill the 1s, we would have 1s2. Then we would move to the 2s, the next energy level, and we'd have 2s2. And then we would move to those 3 p orbitals, and the last 4 electrons would go into the 3 2p orbitals. Now remember, we do have a rule for how those p orbitals fill, which is that they're going to fill, half fill, and then totally fill. So we would go 1, 2, 3, and then fill back to 4. So this is the electron configuration for oxygen, 1s2, 2s2, 2p4, and the orbital diagram for oxygen. But I don't really want to have to do that every single time I make a molecule. That's a lot of boxes and arrows that I would have to draw. So a Lewis structure is going to focus only on the valence electrons. It will ignore the core electrons and the nucleus. So in oxygen's case, the core is this 1s2. It would be the same as our noble gas shortcut. For oxygen, the shortcut is helium, the 1s2. We would ignore the core electrons and nucleus in favor of only looking at the valence electrons. So here's a very important thing to note about Lewis dot diagrams. Lewis dot diagrams are a method of representing atoms only with their valence electrons. It's very important in a Lewis dot diagram to remember we're only dealing with valence electrons. If you don't remember what valence electrons are, don't fret. I'm going to remind you in a second. Valence electrons are the outermost electrons in the highest shell. So if I'm looking for the valence electrons in oxygen, well, I have a 1 shell and a 2 shell. The farthest out shell is 2. So anything in the 2 shell is a valence electron for oxygen. Now, 2 very important things to think about with these valence electrons, because fundamentally, all chemistry is valence electron chemistry. So 2 very important concepts to remember here are that metals are elements which will lose electrons. So the valence electrons in metals are the electrons that are lost in what's called an oxidation. Those electrons can't just disappear. They have mass. They must be conserved. So if metals lose electrons, then nonmetals are the elements which will gain electrons. And they will gain electrons into their valence shell. That's a reduction when an atom gains electrons. The other option in metalloids and nonmetals are that these valence electrons don't lose or gain, but they are shared, which is something that we'll cover later in this unit in more depth. But really fundamentally, all chemistry is valence electrons, moving or sharing. Metals lose electrons, nonmetals gain electrons. Those are 3 fundamental concepts for the next few weeks of this class, that valence electrons are what's most important, metals lose, nonmetals gain. So for oxygen, remember, we are going to ignore our core electrons. We're only going to deal with these 6 2-shell electrons, the 2 in the 2s and the 4 in the 2p. Oxygen has 6 valence electrons. So I'll give you a little hint. If you look at your periodic tables, you'll notice that oxygen is in group 6A. And in fact, that's in group 6A because it has 6 valence electrons. And that works for all of the A columns on the periodic table. The number in front of the A is the number of valence electrons. If you're working with a newer periodic table that doesn't have that old nomenclature on it, you can actually just count across from one side, from the left side of the periodic table over. So I could say lithium, beryllium, boron, carbon, nitrogen, oxygen, 6 electrons because I counted 6 columns over. So to draw the Lewis dot diagram of something, say, which has 6 valence electrons, I'm going to start by putting the element symbol down. So this, I'm just using an X as an example of anything that might have 6 valence electrons. But if I were doing it for oxygen, I could write an O, or I could write an S for sulfur, whatever symbol I need. Then I'm going to draw the valence electrons around this in a particular way. And that's for a reason we're going to talk about in a sec. So what I'm going to do is I'm going to start somewhere. It doesn't really matter, but in this case, I'm going to start on the top because it makes the most sense. And I'm going to draw one dot clockwise around each side of the symbol. So like I'm going around a compass. So there's north, east, south, west. That's only 4 dots though, and I need 6. So now is when I would go ahead and start pairing up. So 5 and then 6. So this element has 6 valence electrons, and anything that has 6 valence electrons should look about like this. Why is it so important that we do this in this particular way? That we draw 1, 2, 3, 4, and then go back and pair. Well, if we look at oxygen, if we draw this and we go 1, 2, 3, 4, 5, 6. Then if you look at what we have in the valence shell, we have 2 pairs, and we have 2 pairs. We have 2 single electrons, and we have 2 single dots. So if we draw the dots in the way that going around, we get a Lewis dot structure that gives us the same information as an orbital diagram in terms of how many pairs and how many single electrons we have. And just like here in this orbital diagram, we would start thinking about adding electrons to fill these empty spots in the p, y, and pz orbitals. Well, we can see here there's an electron that doesn't have a pair and another electron that doesn't have a pair. So we've got 2 empty spots to fill. So remembering this, how many electrons can I put in s and p orbitals? Well, there's 2 in the s, 6 in the p. 2 plus 6 is 8. So the maximum electrons that we'll ever show in a Lewis dot diagram is 8. That's why I always say, can you count to 8 and draw polka dots? That's called an octet. And if you have that vaguely floating around in your head from middle school, this is why. The octet gives me that full low energy configuration. So if I go all the way around and fill the whole thing, 1, 2, 3, 4, 5, 6, 7, 8, I have a full octet. The octet rule is a really great rule of thumb. It is not infallible. There will be rare times that we do actually violate the octet rule. But unless you've got a really good reason, 8 it is and 8 it stays. So the basics of a Lewis dot structure are going to be find the valence electrons, write the symbol, and then surround it, one on each side, and then pairing up. So here's an example for you to try. If we draw the Lewis structure for carbon, we have the electron configuration here, so we need to ignore the core electrons and find only the valence shell. Then we need to add those as polka dots around our symbol. So I give you a second to pause this and try it, and then check your work. So in this case, we have 4 electrons in the 2 shell. So that's 1, 2, 3, 4. 4 electrons around the carbon. Now, am I going to explain to you why this doesn't actually correspond to what we draw in the electron orbital diagram? Yes, next year in AP Chemistry, we'll definitely talk about that. So here are some to try. Again, I'm going to give you a second to pause this and try them, and then you can come back and check your work. All right, well, hydrogen is probably the easiest thing you can possibly do. It's only got 1 electron, so it's only got 1 valence electron. When I get to lithium, lithium is right underneath hydrogen, although it has 3 electrons, but the electron configuration would be 1s2, 2s1. So just like hydrogen, there's only 1 valence electron, 1 electron in the farthest out subshell, the 2 shell. So lithium, in fact, looks pretty much exactly like hydrogen. Beryllium right next to it would be 1s2, 2s2. So that would give us 2 electrons in the 2 subshells. So we'd have 1, 2. Boron would then be 2s2, 2p1. So we would have 3 electrons in the valence shell. 1, 2, 3. Remember, it's also in group 3a, so it kind of acts like a little cheat code. If I want to look at fluorine, fluorine, if I count across the periodic table, is in the 7th box. It's in group 7a. So it has 7 valence electrons, which means I'm almost to as many electrons as I would ever use. So I'd have fluorine, and I would go 1, 2, 3, 4, 5, 6, 7. My last one is magnesium, which, like hydrogen and lithium, magnesium is underneath beryllium. It would be 1s2, 2s2, 2p6, but then we start the 3 subshell, and the 3 then is our valence shell. So we have 3s2, and that means we have 2 electrons in the valence shell, just like we had 2 electrons for beryllium. And just like we had 1 in both hydrogen and lithium. Remember, we said that all the elements in a group have similar chemical properties. And fundamentally, all chemistry is valence electron chemistry. Maybe this is because all the elements in a group have the same number of valence electrons. So we're going to keep going on this in part 2 of our video.